And take it away, Sina. Give me a hand.
Hi, everyone. I'm Sina. Today I'm going to talk about a paper that we recently submitted to NIPS. It's still under review. I guess it's not looking good. The title of my talk is, Can Coarse Coding Solve the Catastrophic and Diffuse Problem? The answer to this question is probably no, but we're going to do it anyways. This work has been done by Janie, Vanasha Rich, and myself. So what is the work about? It's about combining tile coding and neural networks to create reinforcement learning agents that learn fast in a fully incremental fashion. There are 4 important bits to this work. The first one is that I'm going to use tile coding. Tile coding is a specific kind of coarse coding that I'm going to focus on for the rest of the talk. I'm going to combine it with neural networks, and my goal is to create learning agents that are fast and can learn fully incrementally. This is the outline of my talk. I'm not going to assume you know what tile coding is, so I'm going to talk about that. I'm going to have a single slide on neural networks. Then I'm going to tell you how I combine tile coding and neural networks. And then I'm going to show you an experimental result on the mountain car problem. And then I'm going to go through the conclusions, and I'll finish the talk. So tile coding converts a continuous state to a high-dimensional binary feature vector. But how does it do that? Let's imagine that we have a continuous two-dimensional state space, and we have a state inside the state space, which is that small circle over there. I'm going to cover the state space with a grid, a large grid, and I'm going to call that tiling number 1. Tiling number 1 consists of 4 smaller squares. I'm going to call those tiles. Tiling number 1 has 4 tiles, and the feature representation that I'm going to create for that small circle is going to be a 0 because that state is not in the first tile, a 1 because that state happens to be in the second tile, a 0 and another 0. I could stop here. That's a valid feature representation. And that process would be called state aggregation. But I think we can do better than that. So I'm going to go ahead and add another one of those tilings. The red tiling is tiling number 2. I'm going to number that from 5 to 8 now. And I'm going to create a new feature representation. The new feature representation is going to be the old feature representation plus a 0, another 0, a 1 because that state happens to be in the 7th tile now, and another 0. So that's my feature representation. This is the simplest form of tile coding. So I got my feature representation. Let's talk a little bit about the generalization area of this point. So this point is going to have some features in common with all of the points in that blue square or blue tile. It also is going to have some features in common with all of the states in the red tile. But actually, the most amount of generalization happens here. And basically, actually, all of the points in this square are going to have the same feature representation. My feature representation method is going to create the same feature representation for all of the states inside that small square. Okay. Tile coding has a rich history. It's not something new. It was invented by Albus in 1975 as a key component of his CMAC architecture. And believe it or not, this was also brain-inspired. Lin and Kim in 1991 proposed CMAC for TD lambda. And an important thing about tile coding that I would like you to remember is that one of the most important purposes of tile coding was to facilitate local generalization. As you saw in the previous slide, there is no sense of where in the space the state is, but there is a sense of neighborhood and closeness. So what is a neural network? A neural network is a collection of connected units. This is the continuous 2D space that we had. This is our state. It has an x dimension and a y dimension. I'm going to feed this into this collection of connected units. Some magic happens in there, pluses and minuses, multiplication, and it's going to create a feature representation for me. And these arrows are the weights of the neural network. I'm going to show them by WT. It can produce a feature representation. It can approximate a function or other things. And that's as much as I'm going to talk about neural networks. There has been lots of success using linear and nonlinear function approximation. I'm going to mention two of the older ones. The first one is, so tile coding was used with linear function approximation by Rich Sutton in 1996. And he successfully solved a bunch of classical reinforcement learning tasks with tile coding combined with linear function approximation. Neural networks are nonlinear function approximators. Jerry Tezzaro used them in 1995 to create TD Gammon. TD Gammon is a successful backgammon player at the time. Each method has some strengths and weaknesses. I'm going to mention a couple of them here. Linear function approximation with tile coding is usually fast and computationally efficient because it's linear function approximation. But the linear function's expressive power is limited. The number of functions that a linear function can approximate is less than the number of functions that a nonlinear function can approximate. Neural networks, on the other hand, estimate more complex functions, can estimate more complex functions potentially. In tile coding, a weakness of tile coding, I think, is that in tile coding, we designed a generalization. There are lots of design choices to be made for tile coding. Of course, there are lots of design choices to be made for a neural network. There is the number of hidden layers, number of hidden units, the gate functions, the initialization, lots of stuff. But I still think that there are more important design decisions that should be made for creating a successful tile coder. And the last thing is quite important for me. Neural networks, it's a problem of neural networks. When a new sample comes in, you saw a neural network, everything is connected to everything. When a new sample comes in, lots of the weights of the neural network change. And this makes a neural network to try to adapt all of the weights to what it's seen very recently and forget what it's learned in the past. That problem is referred to as catastrophic interference or catastrophic forgetting. And researchers have used ways to work around this problem. One of the very popular things that researchers did, and the researchers do, is that they use a group of samples, a group of observations to update the weights instead of using the last observation to update all the weights. This technique is called experience replay, and it successfully works around this problem. Lots of people use it. Needless to say, it's memory expensive because you need to save lots of the observations that you've had in the past. It's computationally expensive because you need to do batch updates at each time step. But this doesn't mean that this is a solution. I think we still need methods that can learn incrementally and fast. So each method has weaknesses and strengths. How can we choose between them? I don't think we have to choose. I think we can combine tile coding with neural networks. And what's the motivation for combining tile coding and neural networks? There are two motivations from different points of view. The first one is that, as I told you before, tile coding promotes local generalization, and neural networks generalize too widely. So combining these two might help neural networks to generalize more locally, and this might address the catastrophic interference problem partly. Another motivation, which is a totally different motivation, is that tile coding works really well with linear function approximation. We don't have a reason not to combine tile coding with nonlinear function approximation. It might work really well with nonlinear function approximation as well. So we had a simple idea to combine tile coding and neural networks. Pre-process the input by tile coding and feed the tile coding results into the neural network. I'm going to look at that in a bit more detail. So again, I have my continuous 2D space. I have my state. I'm going to call that state S of t. This state has an x dimension and a y dimension. I'm going to feed that into the tile coder. The tile coder is going to create a feature representation for me. It could be of size 4 or of size 8, like the one that I've shown you before. And then I'm going to feed this into the neural network. I'm going to feed this instead of the original x and y into a neural network, and the neural network then is going to create a value function or an estimate of a function for me. This whole thing is my v hat. This is the function. And again, the network weights are shown by wt, and st is my input, so I'm estimating v hat of st and wt. Move on. So now I'm going to talk a bit about my experimental study. I'm going to focus on the reinforcement learning framework. I think you're all familiar with this. The agent is living inside an environment. It's in state S of t at time step t. It chooses an action based on policy pi, and the environment in turn emits a reward rt plus 1 and takes the agent to state st plus 1. And we want to estimate the value function, which is the expected value under the target policy of the sum of the discounted future rewards, given that we start in state st. So we did a simple experiment we focused on single hidden layer neural networks to start with. The neural networks that we used, they all had ReLU gates. ReLU gates are the ones that return 0 if their input is smaller than 0, and they are linear in the input if their input is larger than 0. We compared 3 methods: neural networks as function approximators, tile coding plus linear function approximation, and tile coding plus neural net, which is the proposed method. We used TD lambda to train all of these architectures. And this is the familiar TD error that you see here. This is our function approximator. This is the eligibility trace. And this is the part that's going to be computed differently for linear and nonlinear function approximation. This gradient of the value function is going to be different. We estimated the value function for a given policy in the mountain car task. The policy was set such that it could successfully finish the episode. The results I'm going to show you are averaged over 30 runs. And we used a measure of the difference between the true value function and the estimated value function as the error measure. And for the experiments with tile coding, I had 5 tilings, each of which were 4 by 4 tiles. I'm going to show you the results when I set lambda to 0. We did studies with lambda greater than 0. You're welcome to ask me questions about that. So first, let's look at the classical methods. Tile coding plus linear function approximation was pretty fast. It had a bounce. Neural networks were pretty accurate, more accurate than tile coding plus linear function approximation, but they were slower than tile coding plus linear function approximation. This is the same picture. Just added a new method to it. As you can see, the new method it's pretty fast. It's as fast as tile coding plus linear function approximation, and it's also converging to a good final performance. Yes.
So all these results will depend on the step size for each.
Yeah, I'm going to get to that. Yeah, I'm going to get to that.
Okay.
Okay, so I'm going to zoom in. To the first 100 steps of the previous figure, and what I want you to see is that tile coding plus neural networks it's actually faster than tile coding plus linear function approximation, and it's also faster than neural networks. Yes.
Are you confident intervals on this?
What's that?
Were there couple?
Yes, there are standard errors. You can see a little bit of that on the neural network thing, but the other ones are small. Joseph.
Let's see the previous slide. So I think did the labels change? So on this one, green is tile coding and linear, and blue is neural nets. And
Yeah.
neural nets are the lowest.
Um,
And
Colors
linear-
changed, I guess, to the next graph.
Well, the colors changed, but I was also wondering if the semantics changed. I guess you were limited to the first one.
How did you zoom in on the same graph?
yeah, I'm zooming in.
Okay, so
So
here tile coding is.
the colors did not change. I'm just zooming in.
Okay, so linear has a button, right?
Yep.
Oh, but neural nets also have a button.
Yep.
I see. Okay. And then
Okay.
here we don't.
So I'm going to come back to these during question time, I guess. We also did a parameter study, and that's how we chose the step size. We did a parameter study. The bottom x-axis is the step size for tile coding plus neural networks, tile coding plus linear function approximation, and neural networks. Sorry, I made a mistake. The bottom axis is the step size for neural networks, tile coding plus neural networks, and neural networks. The top x-axis is the step size value for tile coding plus linear function approximation. What I want you to see here, what I want you to see here is that our proposed method has a wide range of step size for which it converged to a value near its best final performance. So I'd like to mention that we introduced another method in the paper. That method is in some ways similar to this method. It pre-processes the data before feeding it into the neural network. One simple form of that method, one specific form of that method, maps the input to the surface of the hypersphere in a higher dimensional space. And just remember that tile coding also is mapping the input to the vertices of a hypercube in a really high dimensional space. This method, the good thing about this method is that it increases the number of input dimensions only by 1. So this is, I'm not going to go through this in detail. I just want to give you a sense of the other method. This is the new method. This is called LP plus NN for lift and project plus neural networks. This is the mountain car control problem, so it's not a prediction problem. This is the new method. This is tile coding plus neural networks. And this is tile coding plus linear function approximation. The y-axis is the number of steps per episodes. The lower, the better. And the x-axis is the episodes. Guess I'm going to give you the seconds to look at this. Okay, moving on. Yes. Okay, you should see that neural network is not learning. Neural network cannot solve the mountain car task. It's such a simple task, but neural networks cannot do it.
Solving it in the previous slide.
That was prediction problem. This is control.
Okay. Right. So, how is new method different in terms of performance than just tile coding plus linear?
In terms of, are you talking about final performance?
Okay, so it gets better earlier than tile coding plus linear.
Yeah, and it also has a different performance in other tasks. You're welcome to look at them in the paper.
It did manage to finish when using a neural network sometimes, right?
What's that?
So you are capping an episode at 1,000 time steps.
Yeah.
So it did manage to finish a few episodes. And actually, you can see at the end, it's kind of getting a little bit better.
Yeah, sure.
Maybe a little bit. So it did learn something.
Sure. Neural networks are good. Not saying that bad. Okay, we move on. So my conclusions, I have 30 seconds. Tile coding and neural networks can be used together. We do not have to choose between them. They can be friends. The combination of tile coding and neural networks actually provided the best of both worlds in our experiments, the speed of tile coding and accuracy of nonlinear function approximation. And after all, neural networks might not be the feature representation methods that do not need any pre-processing. They also might need pre-processing, and this pre-processing might be a part of the solution to the catastrophic interference problem. Thank you. Adam.
I think I disagree with your conclusion too, because if I understand the setup, you probably didn't try to find the best possible tile coder for this domain, or is that what you did?
No, I didn't find the best.
The tile coder that you use and the one you passed in the neural network? Because then the second conclusion isn't really that true.
No, I didn't find the best possible tile coder, but I think you're right. But I think if we make the tile coder better, if we use more tilings, let's say, I imagine that tile coding plus neural networks is also going to improve. That's what I expect to happen. But, yes.
So do you have any intuition of why passing the tile coder input? So like you said, like the global weight changes with the standard input.
Yeah.
So why does the tile coder input not cause global weight changes? Or is that even what is happening?
We have an intuition. So when you tile code the input, lots of the inputs to the neural network are going to be 0. And lots of the weights are not going to change because their input is 0. In the back propagation phase, lots of the weights are not going to change. But when you're doing simple neural networks, this doesn't happen. And so we had other thoughts. For example, these are the outputs of the first hidden layer, output of each node. The color is the intensity. These are tile coding. Those are simple neural networks with ReLU gates. Those are linear in the input space. Those are linear in the input space, but these are like more complex shapes. And if you've seen the mountain car value function, it's pretty much like this. And a ReLU gate cannot do this with a single hidden unit. But a tile coder combined with neural network is able to do it. So this is another possible reason. Martha.
Yes, and I may have misunderstood, but it seemed like at the beginning, one thing you were saying that was negative about tile coding is there are a lot of fiddly bits you have to set up.
Yep.
But, okay, I'm going to play a little devil's advocate here, because with a neural network, depending upon the type, there's a lot of fiddly little bits you have to set up. So now you combine two things with lots of fiddly bits, and they perform better. But what, you've sort of made it more complicated to get it to perform well. I don't know.
Yeah, I think you're right. There is no free lunch. There are more parameters to set. That's for sure. We need to create a good tile coder. We need to play with the neural network. But the thing is that we're also gaining something. For example, if you look at this parameter study, we have to. So the range of step size for which tile coding plus neural network is converging, that range of step size is larger than neural network itself. So you don't have to, for example, play with that many step sizes to find the good step size for which your method converges. But I guess I don't have a pretty good answer to that question. Martha.
I forgot what you said about how the step size is chosen. Is this one step size for the whole network, or did you use something like AMS grad or Adam?
No, one step size, fixed.
Have you considered using something like AMS grad or Adam?
I've considered it, but I haven't had time to do it. So.
There's no reason not to do it, I guess.
No.
Okay, I was going to say one follow-up question to what Tahir said.
Yeah.
Which I think what Tahir said. But the fact that you're inputting this tile coding,
Mhm.
You're saying that fewer weights are going to get updated, but now
Mhm.
what if I have a 3-layer neural network after my top-loaded input? Like slowly, it's not clear that it's going to maintain that locality that you had from the first layer.
I don't have a good answer to that question, and that's, I guess, one of the main reasons we started with single hidden layer neural networks. But I think, for example, the other method that we have, the lift and projecting, that could be applied after each layer. And then that might help, but I'm not sure. Joseph.
So you motivated this by saying maybe it'll help with catastrophic interference.
Yeah.
But we don't really have a good definition of that. And your experiments showed, well, it helped with performance, but does it help with this mysterious catastrophic interference, whatever that is? Could you say something more about catastrophic interference and why you think this helps?
Okay, that's a tough question. So catastrophic interference, I loosely define it. And I think it's happening because everything is connected in this neural network, and when a new observation comes in, lots of the weights change. Neural networks widely generalize, and probably this should not be happening. And I thought that tile coding might be able to help with this, but yes. Yes.
For example, in the control task,
Yeah.
When you do experience replay,
Yeah.
more or less can solve the problem.
Yeah.
Right?
Yeah, she's right. So here, this is, we imagine that this is happening. The neural networks cannot learn because of catastrophic interference. We looked at single runs. This is averaged over 30 runs, but we looked at single runs, and they just go down and they go back up. The learning curves come down and they go back up. And that, I think, means they learn and they forget. They learn and they forget. But the other methods, they just go down and they stay down.
So you actually think experience replay helps with this?
With the catastrophic interference? It works around it, yes.
It makes sense that it makes sense that it should help, because then you don't just update this one thing here and then it wrecks everything. You're forced to update everything at once. So this is sort of has to balance everyone's
Yeah.
needs.
It's like,
Carry on, we'll discuss this later.
yeah, I think Janie has something to say.
So in the paper, we are not saying we are studying
Mhm.
catastrophic interference.
Mhm.
We are addressing catastrophic interference. We are considering interference, learning interference occurring in a single hidden node, which is due to the fact that its activation regions are very global in level 8, for example, and in other similar sigmoid functions, sigmoid gates. And the second comment is that Sina said that second method is kind of similar to the first algorithm, which is to simplify the statement. It's actually very different because it's not, if you think about in the sense whether it's encoding or as far as encoding, it's really not that. It's an embedding. It's a special kind of embedding into extreme points of a convex set. So both methods, why we think they help with reducing the interference of a single hidden node is that because the relocate has certain geometric properties, it corresponds to hyperplanes. And hyperplanes have, and the convex sets have very special properties, and they go together. I will not go deeper into it, which we discuss more in the paper. So the second method is not an encoding method, it's an embedding of the original space. It doesn't create any binary codes, it's not a code at all. So you would have a transformed space which is, other than topologically actually equivalent to your original input space. It doesn't tear apart your space, clustered points at all. In that sense, it's really different. But on the other hand, it shares some similar properties. properties as coarse-conian in that because the space is curved in this way, the relogates would have to work locally in this original space, even though in the input space of which the original space is embedded in, relogates the activation regions of the relogates are still global, but just within that global activation region, only a small part corresponds to the real physical space. So that was the idea of the second method, and we think it's also related to why tile coding can perform better. In a sense, tile coding is not an embedding, but it shares some properties like Sina mentioned, that it maps points to these extreme, like the vertices of a hypercube. That's just 2 comments. Yeah.
Yes.
So can you go back to the last results with like the heat map?
Oh, sure.
So I find this a little bit unfair just because with the tile coding and the neural net, you have these 2 layers of nonlinearity between the input and layer.
Yep.
I'd be interested to see a comparison with a 2-layer neural net, right? For this, and also I guess for the other results as well. But this comparison in particular.
So do you mean for other experiments like this?
Yeah, like I would be interested to see the results for a 2-layer neural net versus.
So I haven't done this for a 2-layer neural network, but I've done all of the others, all these with a 2-layer neural network, and it doesn't change. It doesn't change the results. It doesn't help with the interference. It's not like if we add another layer on top of this, neural networks can solve the mountain car problem.